In this lecture, we're going to learn how we can calculate the enthalpy of a reaction by using bond energies. We're going to use the concept that we just studied previously, and those concepts were that breaking bonds, every reaction involves two steps. The first is that old bonds are broken, and the next step is new bonds are formed. Breaking bond is endothermic, and making bond is exothermic. We're going to use the concept of bond energies. Now, what we mean by bond energy, you don't need to go into a lot of detail if you're in O levels. The concept of bond energy is that it's the energy required to break 1 mole of bonds, and bonds in a particular molecule with everything in its gaseous state. So everything, the molecules and the atoms that are formed, everything is in gaseous state. So that's the concept of bond energy. It's the amount of energy required to break 1 mole of bonds. For example, if you have a hydrogen molecule, in a hydrogen molecule, the two hydrogen atoms are bonded together. And if I break the bonds of those two hydrogen atoms, which are bonded together, I get two individual hydrogen atoms, and so all of them are in gaseous state. You get gaseous atoms. So if I break 1 mole of bonds, the amount of energy that is required, that's called the bond energy. And the bond energies are, you can Google the internet, you can Google and you can find the bond energies for different bonds. They're also given in some syllabuses as well. So if you can just check the bond energy, and just by going on the internet, you can check the bond energy of hydrogen, which comes out to be 436 kilojoules per mole, which means to break 1 mole of hydrogen bonds, 436 kilojoules of energy would be required. Now we're going to use this concept, and we're going to try and find the enthalpy of a particular reaction. For example, I have a reaction in which hydrogen is reacting with chlorine, and it is producing two HCl molecules. Now we can first figure out how many bonds, old bonds, are broken. The hydrogen-hydrogen bond has to be broken in this molecule. So one hydrogen bond is broken. Similarly, the chlorine-chlorine bond in this molecule needs to be broken. So one chlorine-chlorine bond is also broken. So these are the bonds that are broken, and we can then check how many bonds are formed in this reaction. HCl molecule is being formed, so there are two HCl bonds that are being formed. So these are the bonds that are formed in this reaction. We can calculate we can check for the bond energies of these. To break one HH bond, it requires 436 kilojoules of energy, and it's plus 436 because it's an endothermic process. Bond breaking requires energy. Similarly, to break one chlorine-chlorine bond, that requires 242 kilojoules of energy. This sign would also be positive because it's an endothermic process. And bond formation, the HCl bond, the bond energy is 431 kilojoules, but it's going to be minus 431. The reason is bond formation is exothermic. That's the amount of energy that would be released, and there are two HCl bonds that are being formed, so this would be multiplied by 2. We can calculate the enthalpy of this reaction, and enthalpy is the net energy released or absorbed by adding all the energies that are involved in this reaction. First, you would need to break the HH bond, so that would require 436 kilojoules of energy. Then you're going to break the Cl-Cl bond, that's going to require 242 kilojoules of energy. And then you're going to make two HCl bonds, that's going to produce that would be minus 431 into 2. That is going to produce that much energy. And we can we can add them up. It's going to be 678 kilojoules minus 862 kilojoules, and the total comes out to be minus 184 kilojoules, which is your net enthalpy. So in total, minus 184 kilojoules of energy would be given off, and this is an example of an exothermic reaction because the sign of the energy is negative. That means energy is being released in this experiment, in this particular reaction. Now similarly we can calculate the enthalpy of an endothermic reaction, and I'm going to write down one endothermic reaction, which is you have an H2O gaseous molecule and the two H2O gaseous molecules, and it's breaking apart into into two hydrogen molecules, and they're also gaseous, and one oxygen molecule which is also gaseous. And I would try and calculate the enthalpy of this reaction. Before moving on, I need to figure out how many bonds are broken and how many bonds are formed. Now you have H2O. H2O is, you have one oxygen and it is bonded to two hydrogen atoms. And then since there are two molecules, there would be another oxygen bonded to. So these are my two water molecules, and they're getting converted into two hydrogen molecules. In one hydrogen molecule, there are two hydrogen atoms bonded together. In the second molecule, there are also two hydrogen atoms which are bonded together. And you have one oxygen molecule. An oxygen molecule has a double bond in between. So this is the reaction that's taking place, and I'm going to try and figure out how many bonds are broken first. So these are my bonds that are going to be broken because they're not present in the product side. These are my old bonds that need to be broken. So in total, there are 4 O and H bonds that are going to be broken. So these are my bonds which are broken. And what are the new bonds that are going to be formed? The new bonds that will be formed is you're going to have these two hydrogen bonds are going to be formed. So I have two hydrogen bonds that will be formed, and there's one oxygen bond that would also be formed. So these are my bonds which are formed, and I will look for the bond energies now. To break one OH bond, that requires 460 kilojoules of energy, and it would have a plus sign because bond breaking is endothermic, it requires energy, and it would be multiplied by 4. The reason it would be multiplied by 4 is that there are 4 bonds that are going to be broken. Similarly, to form one HH bond, that releases 436, so it's going to be minus 436, and that will be multiplied by 2 because you have 2 bonds that are being formed in this reaction. So that would be minus 436 into 2 kilojoules, and I have one oxygen bond that would be formed, and the bond energy for oxygen is 496. So when this bond is formed, 496 kilojoules of energy would be released. Now I'm going to sum up all the energies involved in this reaction, and that would give me the net enthalpy of this reaction, or the net energy released or absorbed in this reaction. So when I start this reaction, I break these 4 OH bonds, that's 460 into 4 kilojoules, that's the amount of energy required for that. And when I make 2 HH bonds, that's going to release minus 436 into 2, so you're going to have a negative sign because that's the amount of energy that would be released. And you're going to form one oxygen bond that's also going to release 496 kilojoules of energy. And I'll total this, and the total comes out to be 472 kilojoules of energy, and it's an endothermic process because we're getting a positive sign, which basically means that more energy is required for bond breaking and less energy is released when you're forming bonds. So the net energy in this reaction is absorbed, it's taken in. Hence, it's an endothermic reaction. We will now discuss energy profile diagrams for different chemical reactions, and we will take the example that we just did previously. We're going to discuss the energy profile diagram for this reaction. Hydrogen is reacting with Cl2 and it is producing two HCl molecules, and they were all in gaseous state. Now, previously we discussed that the first step in a chemical reaction is that all bonds need to be broken, and we've already calculated the energy required to break the bonds in this particular example. And the energy required to break the bonds, there was one hydrogen bond and there was one chlorine bond, and the energy required to break those bonds, that energy was 678 kilojoules. And two HCl bonds were formed, so the energy required to form those two HCl bonds came out to be 862 kilojoules, and the sign was negative because it was exothermic bond formation. The energy is released in bond formation, so it's exothermic. The net enthalpy of the reaction, or the sum of these two, came out to be minus 1. It came out to be minus 184. So enthalpy of this reaction, delta H, or the net energy released or absorbed in the reaction, came out to be minus 184 kilojoules. Now we're going to construct an energy profile diagram which looks something like this. There's a vertical axis, and this vertical axis represents energy in joules. So whenever you label an axis, you have to write down the unit as well. And your horizontal axis, this axis is going to represent time, or it represents the progress of a reaction. So now we're going to start filling this diagram. The first thing that needs to happen is whenever a reaction starts, it starts with reactants. So I'm going to put a dash. These are my reactants. And the reactants in this particular example are hydrogen and chlorine. And the first step that happens is that energy is required. 678 kilojoules of energy is required to break the bond. So they're going to consume energy. When they consume energy, their energy is going to increase. H2 and Cl2 are going to gain energy, and bond breaking is going to happen. So this is the step where bonds are broken. So your old bonds are broken, they gain energy, and once they gain energy, the net energy of the system increases. So you get two hydrogen atoms and you get two chlorine atoms. Both are gaseous. And the next step is that HCl bonds are then formed, and in this step, energy is released. When energy is released, and in this case 678 kilojoules of energy was consumed, but minus 862 energy is released, so a lot more energy is released, but since it's an exothermic reaction. In an exothermic reaction, less energy is consumed and more energy is released when forming bonds. So this is the step where new bonds are going to be formed, and the two hydrogens and two Cls, they combine together and they give me my products, which in this case are two HCl molecules. So that's basically how you draw an energy profile diagram. Remember that this is an exothermic reaction. So since it's an exothermic reaction, less energy is consumed when breaking bonds and more energy is released when forming new bonds. which in this case you can see that there's only 678 kilojoules of energy was required to break the bonds, but minus 862 kilojoules of energy was released when new bonds were formed. Now the next step is you have to label a few things on this diagram. One of those things is called the activation energy, or it's called EA. That's your activation energy. Activation energy, we can write down the definition of what EA stands for. It's called the activation energy. In simple terms, what activation energy means is that it is the energy that is required to start a reaction. As you can see, in every reaction, the first step is you have to break the old bonds, and only then will new bonds be able to form. So in this particular reaction, energy is first consumed. So every reaction needs energy. And if that energy is not given, the reaction cannot proceed. So for example, if you're heating, if you open your stove and you start and gas starts coming out, there's oxygen available, but they don't react. They only react when you light a match. That match provides the energy, the activation energy, or the initial energy that is needed to break your old bonds. And once they're broken, new bonds can then form, and that is the process that releases energy. So we can, in other terms, what we can say is that activation energy is the energy that is required to break all bonds. I have written that in brackets because the CIE required definition is the first one that I've written. The one that is written in brackets is only for your own understanding. So that's activation energy. I've labeled activation energy on the graph. And the next is enthalpy of the reaction, delta H, which in this case is this. It's the net energy released or absorbed in this reaction. So if you sum this up, this was the energy that was gained. This was the energy that was released when bonds were formed. So the net energy is delta H, where it's the energy difference between the products and the reactants. And in this case, delta H is going to be negative. It's the arrow is heading downwards because it's an exothermic reaction. Similarly, we can draw the energy profile diagram for an energy profile diagram. And we can draw an energy profile diagram for an endothermic reaction. So I'm going to try and draw the energy profile diagram for an endothermic reaction. We're going to take the example that we just did previously, where we calculate the enthalpy of a reaction. And the example was that you had H2O, two molecules of H2O, which were gaseous. So we had steam, and that was getting converted into two molecules of hydrogen and one molecule of oxygen. And the energy required to break the bonds, there were 4 OH bonds that were being broken in this reaction. And once those old bonds were broken, there were 2 hydrogen-hydrogen bonds that were formed, and there was 1 oxygen double bond oxygen that was also formed. So the energy required to break those bonds was it came out to be 1840 kilojoules. That's the amount of energy that was required to break those bonds. And the energy released when forming bonds it came out to be 1368 kilojoules, and the sign would be negative because that's exothermic energy is released when bonds are formed. So we're going to take those two enthalpies and we're going to try and draw the energy profile diagram. So let's start again. There's going to be a vertical axis which is going to represent energy and the unit for energy is going to be joules. And then you're going to have the horizontal axis, which represents time, or it represents progress of the reaction. The progress of the reaction. So we have this. I've drawn the two axes. Now I'm going to start uh, filling this up. We have two molecules of H2O. These are our reactants, and our reactants consist of two molecules of H2O which are in gaseous state. So those are our reactants. Now the first step is bonds are going to be broken. So when bonds are broken, energy is consumed. So they're going to gain energy, and bond breaking is going to happen. So when they gain energy, the energy content increases, and bond breaking happens, and the bonds of H2O are broken. You get four hydrogen atoms, and you get two oxygen atoms, both in gaseous state. And the next step is new bonds will be formed. But in this case, since it's an endothermic reaction, so not a lot of energy is produced. So new bonds are formed, but the energy released in this process, this bond formation, is not that exothermic. So not a lot of energy is released. So these are our products would be written over here. Our products in this case are, we get two hydrogen molecule, and we get one oxygen molecule, which is O2. So that is how the energy profile diagram for our reaction would look like. More energy would be consumed in an endothermic reaction, and less energy would be released when new bonds are formed. The activation energy for this reaction would be, it would start from the bottom and go all the way up. Activation energy, EA, is the energy that is required to start a reaction. It's the initial energy required to break the bonds. So it's going to start from where the reactants are right to the top. And the net energy of the reaction, or enthalpy of the reaction, it's going to start from, it's going to be the difference between the energy levels of the products and the reactants. So we're starting from here and we're ending up over here. So this is our enthalpy of the reaction, delta H, and it is going to be positive. The reason is the products are at a higher energy, which means that in total the reactants have gained energy and then they've gone to a higher energy. So this is an endothermic reaction, and this is how the energy profile diagram for an endothermic reaction would look like. Now in most cases, you're not asked to carefully draw such a diagram. It's not important to write down 4H or 2O. The diagram that is required for Cambridge is, it's a simple straight curve. You don't even need to write bond breaking or bond formation, so you can leave that. The only thing that they ask you to label is the activation energy and the enthalpy of the reaction, and you must know for a fact that if it's an endothermic reaction, the products are going to be at a higher energy compared to the reactants, and if it is an exothermic reaction, the reactants would be at a higher energy and the products would be at a lower energy, since the reactants are going to be releasing energy. So they're going to, the products that are formed are going to be at a much lower energy. We're now going to study the energy profile diagrams and these diagrams would be drawn for catalyzed and uncatalyzed reactions. Now, the first thing that we need to know is, what do we mean by the term catalyst? Now, what does catalyst mean? Now, catalyst is a substance. If you add it in a reaction, it speeds up the reaction. So, catalysts they speed up a reaction. And the way they speed up a reaction is that they reduce the activation energy by reducing the activation energy. And another thing about catalysts is that they remain unchanged at the end of the reaction. So they remain unchanged at the end of the reaction. So that is what a catalyst does. It speeds up the reaction by reducing the activation energy. And remember, activation energy, this over here, that was the energy that was needed to start a reaction. I mean, if I can revise that, activation energy is the energy needed to start a reaction. Basically, every reaction had two processes going on. One was that old bonds had to be broken and then new bonds were formed. So this was the energy that was needed to break those old bonds. So every reaction needs energy initially. For example, if you turn on your gas oven, there's going to be gas coming out. There's oxygen in the air, but they don't react. They only react when you give it energy. When the old bonds are broken, only then are new bonds formed, and that is the process that releases energy. So what a catalyst does is that it makes it easier for us to break bonds. It lowers the energy required to break those old bonds. So I'm going to draw an energy profile diagram for both a catalyzed and an uncatalyzed reaction. So the graph, I'm going to draw it for a reaction which is part of the Haber process. Its Haber process is when you manufacture ammonia. Two molecules of NH3 are formed. The enthalpy of this reaction, delta H, is minus 92 kilojoules. So this is the enthalpy of this reaction. I'm going to draw the graph now. It's going to look, this is my vertical axis. This is going to represent energy in terms of kilojoules, and my horizontal axis would represent the time or progress of reaction. So I'm going to start off with my reactants, and it's an exothermic reaction. So here are my reactants. My reactants in this case are nitrogen, and there are 3 molecules of hydrogen. So those are my reactants, and my products are going to be the products would be at a lower energy. Since it's an exothermic reaction, energy would be lost, and the net energy would be lost, and if energy is lost, the molecules of NH3 that would be produced would be at a lower energy. So 2 molecules of NH3 are produced, and we're going to draw. The first step is energy would be required, so it's going to gain energy to break those old bonds. So energy would be required to break old bonds, and in the next step, energy would be given out or released to form new bonds. So that is my reaction. This over here, I'm going to draw this line over here. This is the net energy released in this reaction. This is the net energy. That would be the sum of the energy required and the energy released. It's the difference between the products and the reactant. So delta H is this, which in this case is minus 92 kilojoules per mole. And my activation energy for this reaction would be, this here would be my activation energy. This would be the energy that would be required to break those old bonds. Now what's going to happen is, for a catalyzed reaction, this activation energy is lower. So that means that the peak of this graph would be lower. The activation energy would be lower. So this red dotted line represents this. And now my new activation energy is this. So there's a lot less energy required to break those old bonds. So the activation energy is lesser compared to the previous case. So my red line is the one that is the graph for a catalyzed reaction. On the other hand, my uh, this represents the uncatalyzed reaction. So remember, the only difference between a catalyzed and an uncatalyzed reaction, if you look at the graph, is that the peak is going to be lower. The catalyst would be, this would be a faster reaction because a lot less energy is required to break those old bonds. So this reaction is going to happen a lot faster, whereas this reaction would be a lot slower because a lot of energy is required to break old bonds. And remember, if for example, if something requires a lot of energy to break the old bonds, those reactions generally happen either very slowly or they don't happen at all. For example, if you want to convert diamond to graphite or graphite to diamond, both are forms of carbon. The activation energy for the reaction is extremely high, which is why some reactions simply don't take place because there's a very high energy requirement to break those old bonds.